I very early developed the philosophy that nutrition was really about two tissues, the brain and skeletal muscle. If those two tissues were healthy, you were going to live a pretty good life. Everything else is regulatory, the liver, the heart, the kidney, the gut, everything else adapts to your environment, but you have to focus on those two. And I think if you tailor your nutritional requirements around that thinking, you end up with a much more sensible approach. And I sort of coined the concept that my colleague, Dr. Gabrielle Lyon, and I always use of muscle-centric nutrition. And if you keep muscle healthy, you've got a good shot at avoiding obesity, avoiding diabetes, avoiding cancer, et cetera, et cetera. Muscle really serves two functions. One, the obvious one, is mobility. Most people get to the age of 65. Beyond that, most people actually die from some form of immobility, falls, breaking something, hospitalization. So functional mobility is critical. But the other aspect is metabolism, and muscle is a primary site for insulin activity. You mentioned glucose storage. I look at it more as an issue of glucose utilization and also fat utilization. So basically, your blood glucose and your blood lipids are heavily, obviously the amount you eat makes a difference, but the actual level is heavily dependent on your muscle metabolism. And you sort of commented about insulin resistance being associated with fat. Actually, insulin causes insulin resistance. So if you chronically elevate insulin too long, that is the definition of type 2 diabetes, is that basically insulin causes insulin resistance. So the question then becomes, which one's more likely to be physiological? Because people are eating 350 grams of carbs per day, or because they're eating 90 grams of fat per day. Which one's likely to cause it? Bob Wolfe, there's a philosophy called the Randall hypothesis. I don't know if you've heard of it.
Yep.
But basically the philosophy is, the Randall hypothesis was that fatty acids, the diacylglycerol, cause all the problems. And what Bob Wolfe did was basically run that experiment with stable isotopes, and he showed it's actually the reverse, that fatty acids are not inherently toxic, but glucose is. It has its own disease. We call it diabetes. And so when you eat excess carbs, you must get rid of them. You absolutely have to dispose of them in the next 2 hours. Or fat basically can hang around for much longer. It's just simply not that toxic to the body. In fact, the body always wants a certain level of free fatty acids in the blood because that's the fuel for the heart. You always want to think about it as that carbohydrates, excess glucose is toxic. If the blood level is high, you'll damage basically every tissue from your eyes to your toes. Yep. And so you have to dispose of the glucose. So Hellerstein's, what he showed was that if you have a diet that's, say the American diet, 50% carbs, 35% fat, and you take in 1,000-calorie meal or 800-calorie meal, which one are you going to put into fat quickest? You're going to put in the easiest one, the one that's already fat.
Yep.
And so the carbohydrate's going to get burned and the fat's going to go to fat. It's just simply the body is selecting the easiest pathway. But if you switch that, and Jules Hirsch did it, and then Jeff Volek did it later, if you switch that to a 80% carb, 10%, then you'll see that de novo liposynthesis. And one of the interesting things out of it is when the body makes fat, the only thing it can make is saturated fat.
Yep. Palmitate.
So we have a lot of saturated fat in the blood that actually doesn't come from eating fat, it comes from eating carbs. Important for people to realize we burn around 100 calories per hour. That would be 2,400 calories per day. So 100 calories per hour, in a 2-hour period, you're only burning 200 calories. So everything else has to be stored. That takes us into a protein discussion, and I would say absolutely not. Two angles to that. One was there was a theory back when I was early in my career, back in the mid 80s, by Gil Lavelle, and he was arguing that lots of small meals was good for less fat deposition. And it was an artifact of how he did the study. He did it with animals and basically showed that when you made the adaptation to lots of small meals, the animals didn't gain as much as if you adapted them to like 2 meals per day. But the artifact was when you adapt an animal to 2 meals per day, they go through a starvation period because they have to learn to do it. And when you come out of a starvation period, you're making more fat. So we redid it with a longer adaptation period, and what we found was that reducing the number of meals per day actually is thermogenically advantageous. You actually waste more calories. The other aspect we can get into is protein. Protein needs to be distributed at specific meals. The distribution needs to be high, and eating lots of small meals is a really bad choice for a lot of reasons. Talking about a protein requirement just reflects ignorance. We have specific requirements for 9 essential amino acids, and that gets into the complexity then, because these amino acids are essential for building blocks for new protein, but every one of them has a metabolic role, like leucine and mTOR, or arginine and nitric oxide, or lysine and carnitine, or cysteine and glutathione. And all of those roles are vastly above the minimum that is detected for nitrogen balance for the RDA. And so that's where people fall apart, is that we think about vitamin C and we know there's a minimum RDA to prevent scurvy, but people will take 5 or 10 times that during COVID for immune response. But we resist thinking that way about amino acids, and it's exactly the same. Yeah, so a little bit like a fatty acid, an amino acid has a carboxy end connected with a carbon, and then it has a nitrogen end. And when the body is so when we eat protein, we get these amino acids in some sort of a string, but we totally digest them down to probably individual amino acids, maybe di or tripeptides, and we absorb them that way. They get to the blood as single amino acids for the most part. And then the body begins to reconnect them based on the messenger RNAs. Our DNA tells us how to reconnect them. And so we connect a carbon to a nitrogen and we string them together. Of these 20 amino acids, though, they all have that acid and nitrogen part, but they also have a side chain, ranging from very simple one like glycine with just a hydrogen to ones like tryptophan that have a big aromatic part to them. And so all of these are different, and they go into proteins in different structures. The DNA tells us how we put them together, and proteins can be simple like insulin with 51 amino acids, or they could be like myosin with thousands. And so they're also, and then every protein in the body has a different turnover rate. Some of them, like insulin, might last 15 minutes, and some of them, like myosin, or we'll just take collagen, might last. But beyond that building block structure, then every amino acid has other kinds of structures. It might be like lysine, where part of it becomes the molecule known as carnitine, which is for fatty acid metabolism, or it might be the nitrogen off arginine that goes to nitric oxide for vasorestriction, or it might be cysteine, which goes to part of creatinine or glutathione. So we can get to leucine, which is sort of my favorite, which is a signal, which really got me interested in protein and metabolism, is a signal for muscle protein synthesis. So again, they all have this building block structure. They get strung together in different links. But they also have other metabolic functions, and that's what people don't recognize when they're talking about protein requirements. The argument is that for all RDAs, we sort of test a population and come up with an average number, and then for a safety factor, which average would be 50%, would be deficient. And so we add a safety factor of 2 standard deviations, which supposedly 97.5% of the people would be adequate to prevent any signs of inadequacy at that point. But that also means 2.5% of the people are actually deficient at that point. So that's sort of the definition. Where does the RDA come from? I think it's useful to go back in history just a little bit then on protein. How did we begin to evaluate protein needs? Well, it all came out of animal sciences. Back in the early 1900s, before we even knew all the essential amino acids, farmers were trying to say, how do I get animals to grow best, and different kinds of proteins and things like that. And they developed protein quality scores and things like that. So how much growth did I get for what I fed? How much nitrogen did I deposit for how much I fed? So these were all rapidly growing animals, and we developed this concept really of nitrogen retention. We've now translated into what's called nitrogen balance. That's how we determine the protein requirement. All of the concepts were developed for growth, where nitrogen balance was positive. You could measure a change over time. And as we've now tried to start applying that to non-growing adults, it gets a lot more vague. Everyone who knows nitrogen balance says that nitrogen balance underestimates requirement. Everybody, uniformly. But that is where the RDA comes from. And when you do short-term studies, what you find is most people, young adult, and again, all these studies were done with college-age students, so they're kind of right at the end of their growth. In a short-term 7-day study, they look okay. So that's where we're at. In the last 20 years, those of us who study protein have gone beyond that and said, well, nitrogen balance is one outcome, but like the vitamin C argument, there are other outcomes based on amino acid metabolism that may be more important than minimum nitrogen balance. And we now know that protein handling goes down, the efficiency goes down as we get older. So now we have much higher requirements that most of us talk about for adults. For the most part, knowing essential fatty acids, carbs and fats are basically energy sources. They're carbon-carbon bonds that provide energy, where amino acids have a very different purpose and structure, and that nitrogen is part of what makes them different. If you're looking at animal source proteins, whether it's meat or eggs or milk, basically all of the amino acids that a human would need are in those, because they're basically, obviously a chicken's not a mammal, but the others are mammals, and basically we have the same amino acids, the same proteins. So they're all there. Meat is a good example because they're all pretty much in the right balances. Basically, we realize that when you look at a protein, there are two factors. One is what's the composition of those 9 essential amino acids, and the other is what's its bioavailability? How well do we digest it and absorb it? Animal proteins and most isolated proteins, even soy protein isolates, the digestion absorption is pretty close to 100. It's usually 95% or higher for all animal proteins. For plant proteins, though, it gets into, you need to realize that in a plant, the protein is there for the purpose of the plant. And so a lot of it is attached to fibers, to structures. Plants have proteins attached to the leaves and the stems and the roots and the flowers and the seeds. And when you start to isolate that, if you just eat it in a raw form, it may only be 60-70% available because we can't digest the fiber. So those are the two factors. We can put those two together and get a protein quality score, and we can determine that a whey protein isolate, because of its essential amino acids, is 20% better than a soy protein isolate, just because of the amino acids. Or we can compare a wheat protein, a wheat bran, and we realize that it's only 40% available. So if you look at wheat bran on a cereal box and say it was a wheat flour, and it says there's 4 grams per serving, there's actually less than 2 that you can actually absorb. I am working on with a group trying to build a protein quality score that really based on 3 amino acids, lysine, methionine, and leucine, which in my opinion are the key markers for adult health. I mean, if you go into the USDA database with whatever, 7,000 foods, there are 4,000 that actually have amino acid scores, and of those, there's probably less than 300 that have DIAZ scores. And so you can't put it together. If you look on a label on a package and you see, again, a wheat cereal that says it has 4 grams of protein, well, again, that's a nitrogen analysis. And then if you look over in another column, it'll say daily values.
Yeah, exactly.
And there almost no label have daily values for protein because that would require a PD-CAS or DIAZ score, and nobody has them. And so that 4 grams really would translate into less than 2, but nobody's being told that. But I have a big problem with the amino acid scores because they're incredibly low. They're way too low. And so they're established by the World Health Organization, by the FAO, which is really designed to prevent malnutrition in Africa, where we know from our Institute of Medicine that the essential amino acid scores are much higher than that, should be. You mentioned stable isotopes a little bit ago, or tracers. We know from stable isotope studies that all those FAO amino acid scores are too low. And so that's part of the equation that we're not telling people either.
Hey, what if we make this easier and you focus on the actual content of 3 amino acids? So we're going to take a subset of essential amino acids, methionine, leucine, lysine, and we just want you, Peter, to walk around and make sure you get enough of those with each meal. And if you do that, the rest will take care of itself. Is that effectively what you're saying?
That's exactly what I'm saying. If you look at DIAZ scores right now, the amino acid scoring, I've already said is too low, but if you look at how they're scored, they're not scoring apples and apples, they're scoring apples and oranges. All legumes, like soy or pea, are limiting or deficient in methionine. And you score that against whey, what you end up is the limiting amino acid in whey is considered histidine. And no one has ever shown histidine to actually be a limiting amino acid in an adult. It's a limiting amino acid in children, in babies. So if you compare methionine to methionine, it's not 20% higher, it's 250% better. Apples and apples, we need to compare them across the 3 essential amino acids that are actually likely to be limiting. So now we've got an issue of mTOR and whether it needs to cycle on and off. And not only does leucine turn it on, but so does insulin.
Yep.
And so probably the worst case scenario, and you can use a lot of animal studies to back this up, would be people who eat a lot of small carbohydrate meals that continuously activate mTOR. What we want to do is use specific meals with the right amount of insulin to activate muscle-centric mTOR. mTOR is in every tissue, and what you don't want to do is continuously activate it in liver or some other tissue. And so that's where the confusion gets into Absolutely. It, is people ignore the fact that insulin is just a biggest trigger in other tissues, where leucine's a very unique trigger in muscle. If you look at limiting amino acids actually in food, lysine is always limiting in grains, and that has been shown in animal science over the years. That's a major limitation in how you feed, what the minimum amount. So that one is probably limiting for protein synthesis. We need about 3.4 grams of lysine per day. We need probably a little less than 1 gram of methionine. So they're not in the same proportion either. But the methionine is what we call part of the 1-carbon pool. And so basically for the body to make and repair DNA, to make and repair RNA, to make taurine downstream, to make the non-essential amino acid cysteine, to make glutathione, the oxidant, Methionine is the key to all of those pathways. Methionine is one of the most limiting, and it's limiting in all legumes. So we think of soy and pea and a lot of, and lentils and things of that nature as higher quality protein. They are, but they're still limiting in methionine. The classic one of, quote, sulfur amino acids is eggs.
Eggs, yeah.
Eggs are quite high in the sulfur amino acids, which are methionine and cysteine. Yeah. But all animal products are adequate in them. And And basically all plant products are pretty low in them. Cattle, ruminant animals, are a very important part of the food chain because of their stomach, which is full of bacteria. One of the things to think about for essential amino acids is really the only place they come from in life is bacteria. Our primary source of them in nature is the bacteria on roots of plants. So the bacteria on the roots will take the nitrogen. Why do we fertilize our garden? Is nitrogen. The bacteria will take that inorganic nitrogen and form organic amines with it. And those organic amines then can be made into proteins in the plants. The problem with plants is that they don't have the same balance as we need. They have the plants to make roots and limbs and roots and flowers and things like that. The beauty of a ruminant is they can take that plant and they can digest it, and the bacteria then will rebalance all of the amino acids. They'll capture inorganic nitrogen, and they make the essential amino acids that mammals need, and they concentrate it for us. So basically humans, one of the arguments is humans evolved by being able to use more concentrated protein. If we just ate plants, it's hard to get enough. Basically for every 60 grams of protein an animal eat, they'll make 100 grams of essential amino acid, balanced protein. So ruminants are called upcyclers. So whether it's in dairy or meats or, also, goats and sheep and deer, all of those ruminant animals upcycle. By eating grasses, they produce great quality protein. No other animal can do that. They're making protein out of nitrogen.
That's right. That's what I was going to say. So they're getting the nitrogen from the fertilizer that went into the grass. And
not quite. They're getting nitrogen that's inorganic in the plants, but it's not actually in protein forms.
Yep. Okay.
And so it's in the fibers and other kinds of things. So they're able to upcycle that. They're able to increase the value of non-amino acid nitrogen, plus they capture all of those other nitrogens. The bacteria, if you look at the flora in the cow, they have certain bacteria that will produce methionine or lysine. It's important to recognize that whether you're 16 or 65, your body needs to make nearly 300 grams of new protein per day. So there's a protein turnover. Every tissue in the body is turning over. Some as fast as liver enzymes we replace every hour. Muscle proteins we replace with half-lives of around 15 to 16 days. So every 30 days. Collagen turns over at about half-life of 100 days, which is why if you hurt your knee, it takes so long to repair it. The body replaces literally every protein in it about 4 times a year. And then if you think of we have to make 300 grams of new protein per day, the average American intake is around 80 grams or less. Women 70, men 90. That means that there's a recycling thing going on. So of every new protein that's getting made in the body, about 6 out of 7 amino acids are getting recycled. What we now know is that as you get older, the efficiency of that protein turnover goes down. So where a 16-year-old, you give them a certain amount of protein, they'll have a very good response. A 65-year-old will have maybe no response at all, or 10% or something. But what we have learned, sort of with the study of leucine and initiation factors and all of that, is that if you give an enriched source of essential amino acids, you can actually make the adult look just like the 16-year-old. So what we know is that the efficiency goes down, but the capacity to respond doesn't. What we now know is that if you have a requirement that's about twice the minimum RDA, so instead of 0.8, it's 1.6 grams per kg, we can get the adult, the 65-year-old, to respond just the same as the 20-year-old as far as muscle protein synthesis. Most people who go to a plant-based diet, a vegetarian diet, decrease both the quantity and the quality. If you're on a plant-based diet, you'll need more protein, and that means you'll have to have more calories. But what's the threshold for that? What we would probably argue is that if you have 120 grams of protein per day, it probably doesn't matter the distribution between animal and plant because you probably have enough to cover it. If you're only eating 50 grams of protein per day, then it makes a big difference. You'll never catch up to your essential amino acid needs. So somewhere between 50 and 120, it depends on what you choose. There are 4 different signals that regulate mTOR. We've mentioned leucine. We also mentioned insulin. An enzyme, a factor known as AMP kinase, which is carbohydrate sensitive, is energy sensitive, and then another molecule known as RED1, which is stress sensitive, particularly resistance exercise. So there are 4 different things the individual balances. When you're young and growing, insulin and IGF-1 dominates that. And insulin, first and foremost, is a growth hormone. And when you stop growing at 25, it ceases to have an effect on protein synthesis in muscle. And so now the whole thing shifts to protein quality. Protein quality is not nearly as important when the system's dominated by hormones. And so now what we know is as we get older, we can buffer that loss of the hormones by higher quality protein, mostly leucine, and resistance exercise. Those 2 factors will balance out the growth issue that young people have, the benefit of the growth part. The issue with protein is being an absolute number. If your calories go down, say you're now a 75-year-old woman and your calories per day is now 1,200 calories, you still have a 100 gram per day protein requirement. If people are doing weight loss, it's an absolute number. So people should never talk about percentage of calories. You have to think about protein first. From my research, one of the things that we believe is that the most critical meal of the day is the first meal of the day. When you have had an overnight fast, your protein synthesis is down and that mTOR signal molecule is downregulated, it's inhibited. And until you have enough leucine, around 3 grams, which translates to about 30 grams of protein for most people, until you have a meal that has 30 or more grams of protein, your muscle stays catabolic. So you're continually breaking down protein. We think that's a significant aspect of aging, that people have lower and lower protein, they don't eat protein at breakfast, and we know the efficiency is going down in the first place, so we want to front load protein in the day. So we want at least 2 meals that are well above 30 grams of protein. So I always have people shooting for 40, 45 at the first meal, another 45, 45 at their last meal. Let's say an elderly woman trying to maintain minimum muscle, I'll concentrate on those 2 meals. If I'm talking with somebody who's trying to do weight loss, I'll concentrate on 3 because I don't want them getting hungry. If I'm talking with someone who's trying to be hypertrophy, a muscle builder, I'll concentrate on 4. So how many meals per day do I make anabolic and muscle? And by anabolic, I'm thinking 35 grams or more. So we're talking about adult protein needs, and I don't want everybody to walk away thinking, gee, I need to get 50 grams of protein in my kid. Yeah. Children will be very efficient at maintaining growth with small snacks of 8 to 10 grams of protein, where that will have virtually no impact for an older adult. So, a protein bar that had 10 grams of protein is a perfectly legitimate snack for a child. Let's say we have 100 grams of protein, but we take it in very small meals, 15 grams. Yeah. Trickled in all day long. You will never stimulate muscle protein synthesis, but your liver will be perfectly fine. Your gut will respond to that amount of protein. Your gut, your liver, your heart, your kidney, all of those organs will respond to the net protein per day no matter when you ate it. Muscle isn't triggered unless the diet is exactly right. The muscle senses energy, insulin, protein before it triggers, and if all of those aren't balanced, it won't trigger, but your liver will. You know, your liver, your heart, those have to function, you know, middle of the night, your liver still has to be making protein.
Yeah.
But your muscle doesn't. While you're laying there in bed, your muscle is catabolic and it's supplying amino acids so all those other organs work. And plus his protein synthesis, as we mentioned earlier, is driven by hormones, where yours isn't. So
good point.
His growth is highly efficient. It's driven by hormones, and he'll accommodate it in small doses. And you're right, he probably only needs 45 for the day anyway.
Okay.
And so we were looking at what were called initiation factors, and we discovered the link between leucine and an initiation factor called EIF4. And that is sort of the downstream effect of mTOR. mTOR is a regulator, and it stimulates EIF4 and S6 and other initiation factors. And so what we found was that when you came out of an exhaustive exercise, muscle is catabolic until you took in enough leucine to reverse it. The biggest effect of feeding right afterwards is about a 2-hour window, but that's in untrained individuals. The more trained you get, the less you're going to see a post-exercise effect. So if you're beginning training, you're in the first 4 weeks, post-exercise protein probably makes sense. If you're well-trained, you're basically training the same way and you've been doing it for 6 months, I don't see any difference between having protein within 2 hours after exercise versus just having your 3 or 4 meals per day. You won't see any difference in either mass or strength. Take that last statement, metabolizable energy, and you'll hear trainers say, well, you can't use more than 30 grams at a meal. You won't digest it or whatever. That's not true. I mean, you'll digest and absorb 100 grams of protein at a meal, but muscle in particular only has a window of around 25 to 60, depending on protein quality, where it can use it. The liver will use all of it. When you eat a meal of protein, approximately 50% of the protein is degraded to nitrogen and carbon before it ever gets to the blood. The exception to that are the branched chain amino acids, leucine, isoleucine, valine. Over almost 75-80% of those get into the blood, and we're back to that teleological argument. Why did muscle learn to sense that? Because that basically shows up in the blood in direct proportion to the meal, and the muscle learned to sense that as a meal quality. It says, oh wow, this meal has adequate quality for me to trigger this very expensive process of protein synthesis, protein turnover, and until it sees that signal, it won't do it. And so leucine is one of really 2 amino acids that are ketogenic. It is metabolized as a fatty acid. And what we know is that leucine will also activate the CPT1 enzyme, the carnitine palmitate transferase enzyme, which is the link of bringing fatty acids into the mitochondria for oxidation. When you have higher leucine, it also begins to inhibit pyruvate from going into the mitochondria. So when you oxidize a leucine, the nitrogen that comes off of it is put onto pyruvate, generating an alanine, and so the body begins to recycle glucose. So it becomes kind of steady state on glucose and emphasizes fat oxidation. Under conditions where you'd be burning fat, like you just described, leucine actually stimulates fat oxidation and spares glucose for the brain and other tissues. So the well-controlled one, what we found was that with the higher protein, and as far as we could measure exactly the same calorie intake, the people on the higher protein, low carb lost more total weight, more total fat, and less lean, and that stabilized their insulin and glycemic regulations and lowered their triglycerides across the board. So both groups lost weight. They were both on weight loss diets, but the protein people lost 8 pounds more, and almost all of it, something like 6.5 of it was fat. And one of the things that the dietitians who were running the study always came back is they said that the protein people were never talking about food and snacks, but the people on the high carb diet were always talking about being hungry and snacking. It definitely partitions the weight loss toward fat, protects muscle, the lean tissue, definitely has higher satiety. We want weight loss, but we don't want people to lose any lean mass, especially if they're adults. If you're a 20-year-old, it probably doesn't matter so much. But if you're older, if you're beyond 40, it does matter. In the same period of time, an older adult in bed rest will lose 4 times as much muscle as a younger adult. It's frightening how fast you can lose it. And if you're diligent and do weight training, you can begin to gain it back, but it's hard to ever get back to ground zero. All this leucine stuff, when does it really come into play? It's not as important for a 20-year-old as it is for a 60, but where's the middle ground? Where does it change? And I think it's a little like bone health. I think once you're 40, you're sort of on the back end of that, and you need to be much more careful. Took 90 grams of protein and looked at it distributed as 3 meals per day, 30, 30, 30 versus 10, 20, 60. And we found that with the same amount of protein, the same overall diet, you would have higher net protein synthesis with the distribution to breakfast. I think the first and last meals are the key.
Okay.
But when you trigger mTOR at that first meal, we know that it's still stimulated 5 hours later. So why do you need leucine for mTOR at lunch if it's still stimulated? You don't.